Let's talk about this. And the most important aspect is today, companies like Microsoft and American Express are, and again, these are just two examples, who are leveraging our deployment platforms, namely Triton and TensorRT. And the whole plan is that, if you want to do very low latency inferencing, and still, get the same performance with low inference response time, and again cutting down the CPU cost time for doing the inferencing, GPUs are a very good option. And for use cases like grammar correction that you see on Microsoft 360, these capabilities are being used over there for grammar correction. And again, it leverages the Triton inference server for doing all of this. The second example is American Express. And basically what we did was, American Express had this use case of real time fraud detection. And what they saw was, they were getting approximately 100 to 150 milliseconds of performance. But for a use case like real time fraud detection, this is not really a very good SLA. What they were looking for is to get the latency around 1 to 2 milliseconds on top of the system. So what they did was they took their LSTM based model, applied TensorRT optimization, and deployed it on Triton. And with that, we were able to achieve the latency of about 1 to 2 milliseconds, for each of the transaction, which was again pretty great, because now they could have this platform be deployed in real time as well. So yeah, so these are two of the biggest success stories, and American Express is something that is very close to me, because I was personally involved in this deployment. So let's talk about what TensorRT and Triton is all about. So let me give an generic inference server deployment architecture. So what we see today is there are going to be a lot of clients that are going to request for the are going to send some data. And what we need to do is we need to accept that request and basically process that request, and give back some output. So how that happens is, these multiple clients are going to get connected to the servers. And here, basically on the first level of the servers, you essentially have a lot of these clients which will be talking to Triton. And all of these clients now are going to have a load balancer between the inference server and the client itself. Right. And basically what happens is that there is going to be either an HTTP or a gRPC request that the client can send to the inference server, and accordingly the inference server is going to reply back with the corresponding output or the payload. Now, there are two things to consider here. One is deploying these deep neural networks and serving them as API, which is the server part. And second is optimizing it before serving it on the Triton. So what you see on the topmost right side is you have few models. Again, could be optimized, could not be optimized, and then you basically run the Triton client on top of that. Now what happens is you can either have it in PyTorch or TensorFlow, or you can optimize it using TensorRT for best performance. So these are the these are the couple of options through which you can deploy your pipeline: PyTorch, TensorFlow, Onyx, TensorRT, whichever model, whichever framework works best for you. But for best performance in terms of low latency and high throughput, TensorRT is a very good option. Then all the metrics basically goes to a metric server, where the utilization as well as how much GPU is being consumed, plus what is the compute time and the response time, all of that gets stored. And once it grows grows above a particular threshold, the Kubernetes cluster or the autoscaler will essentially spawn more of such Triton servers to balance out the payload. Um, Now, to talk about Triton basically, along with TensorRT, is the best scale out, way of scaling out your deployments across your clusters, right? So we have this GPU called the T4, which again is specifically meant for inferencing, and again has a very small power watt to watt ratio. Sorry, performance to watt ratio, which is about just 70 watts. And then again, it almost provides very similar performance to a V100, not completely same as a V100, but about zero point 0.5 or 0.6% of what a V100 can provide. And then you have the TensorRT compiler that is going to do some graph based optimization and another optimization that we'll talk in detail. And using Triton, you can take the models from PyTorch, TensorFlow, Onyx, or TensorRT and deploy them at scale. So let's first look at TensorRT and what exactly is TensorRT. So basically, it's a compiler technology built by NVIDIA, and what we know is, see, there are different GPU architectures. So the Tesla T4 is based on the Tesla architecture, PX2 is based on the Pascal architecture, V100 is based on the Volta architecture, and then we have the Ampere architecture. Now, each of these architectures, the way the SMs are built, it becomes very crucial to have custom CUDA kernels for each of these, devices. Now, point being here is that when you take your model from either of these frameworks like PyTorch, TensorFlow, or any other, and when you want to optimize it for the target hardware, the optimization is also GPU architecture specific. That means, to get the best performance, if you have compiled a TensorRT engine on V100, that will not work on a T4, because the target hardware level optimizations will be different for the T4 architecture versus how it will be for the V100 architecture. So again, it essentially tries to create these engine files which are GPU architecture specific, and and they are really highly performant as well. So now let's look at some of the optimization that it does. The first is quantization. So basically what this means is, usually for training we use FP32 and FP16, but that is not the case every time, especially for inferencing, because TensorRT is not meant for training, it is specifically meant for inferencing. So people tend to use FP16 and integer 8. Integer 8 comes with some degradation in the accuracy loss, but FP16 works pretty very exactly comparative to FP32 in terms of the inferencing capabilities is concerned. The second one is layer fusion. So you remember when we talked about these ResNet architectures, you saw multiple blocks of convolution batch number, right? And what that means is, how about I combine these layers rather than calling the CUDA kernel for each of these layers separately? Can I combine these three CUDA kernels together and then launch it, so that it will basically save me the time for calling three different functions? So layer fusion will apply a lot of different graph level optimizations to make sure that whatever operations which are there, consecutive operators which are there in the entire acyclic graph, if they can be combined together as a one operation to make the graph much smaller and more optimized. The other ones are kernel auto tuning. So like I said, every target hardware will have a different GPU architecture, and hence the best parallel algorithm, that means the best CUDA kernel for that target architecture will be very different. So what TensorRT will do is it will try to tune and find the right most optimal CUDA kernel for that target hardware. It also does other things like dynamic tensor management as well as multi-stream execution. That means if you have parallel streams coming in, how can I use all those streams together and do the inferencing with the TensorRT engine? So let's look at the graph optimization. And again, the best example here is ResNet 152, wherein there are about 670 operations in total. And after you do the TensorRT optimization, you'll only have 159 layers. So there's a huge number of reduction in the number of graph operations which are there, which TensorRT essentially does. So the non-optimized graph that you see on the right, you see that conv bias relu basically is going to get is going to get clubbed as a single function, single CUDA kernel. So as you can see here, we have these fused CUDA kernels which are available to us. So all the 1x1 conv bias relu are being are being made as one cross one CBR layer, and all the other 3x3 and 5x5 are again combined together as one entire kernel operator. Right, so that is how TensorRT is going to optimize these specific layers based on what can be optimized. And if you look at the throughput, there's a huge improvement in terms of the latency compared to running it on top of either CPUs or on a native TensorFlow as well. Now with Triton, what really happens is it provides you the capability. So you have different frameworks which have their own deployment frameworks like TensorFlow serving or even PyTorch serving. But if you actually see, it does not, I mean, they don't have interoperability between different frameworks. But if you look at Triton, we are framework agnostic. That means we support any of the frameworks that you want to use for deploying your workloads. Second most important thing is you can have multiple models deployed on a single GPU. That means if you have a 32 GB card and if the model inferencing only takes say 5 GB, you can still load more models on top of the GPU as well. So it provides you with complete capability to do that, so that your GPU resources are not being wasted. Right. And these are some of the capabilities that it has, right from dynamic batching to concurrent model execution. And I'll quickly show you how to do the TensorRT conversion as well in the hands-on demo. So some of the other important parts also of Triton is that it serves you with two API endpoints. One is the HTTP and the second is gRPC. And you can either run it on, you can basically call the client and either call the HTTP protocol or the gRPC protocol. And you can seamlessly scale it across multi GPU, and you can also run it on CPU if needed. So with that, I'll quickly show you how to do the TensorRT conversion and do it for FP16 and FP32. Yeah. So just give me a second. Let me share my Jupyter notebook. Okay. So what I've done here is I'm simply going to take a ResNet 50 pre-trained model, right? And I'm going to call something called onyx dot export. So first thing that I'm going to do is I'm going to convert the model from PyTorch to Onyx. And to do that, it is pretty simple. You just pass the name of the input node, output node, and the dynamic axis, which is basically the input and the output as well. And you basically give the model, you pass some dummy inputs. So the dummy inputs here could be basically be a simple torch dot random tensor of shape 3 comma 3 comma 250 224 comma 224. Okay. And you can parse this, and you simply pass the model dummy input name of the model verbose, just to see just to get some understand if everything is working fine or not. Input name, output node name, and the dynamic axis. So let's quickly do this. So there's a question, what is the difference between tensor and TensorRT? Great question. So tensor is basically a four-dimensional ND array. Sorry, not a four-dimensional array, but rather a n-dimensional array, right? And so basically tensors are very similar to arrays. It can have n dimensions, but the capability that tensor has is the fact that it can run on CPUs, GPUs, or even any other accelerator like TPUs. And if you look at TensorRT is a compiler. So tensor is just a normal term used for defining a n-dimensional tensor that can work on any accelerator. But TensorRT is a compiler technology built specifically for GPUs that takes a neural network architecture and does GPU target level optimization for maximum performance. So it has to do more with the optimizing the entire computational neural graph, and doing a lot of different optimization like layer fusion, precision calibration, as well as dynamic memory management and multi-streaming support, and kernel auto tuning. The next question is, what is Open NMT? It basically stands for Open Neural Machine Translation. So it is one of the models which is available. Okay, so here I've converted my model to Onyx, as you can see here, right? It has been created. Now the next step that I need to do is I need to convert this to TensorRT. So there is this utility called TRT-exec, and what I'm going to pass to that is the Onyx model. And what I want to do is I want to give some minimum shape, optional shape, and maximum shape. Now the reason why this is important is because when you compile this model on TensorRT, essentially you need to provide what is going to be the maximum batch size. So in this case, my maximum batch size, excuse me, my maximum batch size is going to be 32. That means I cannot take any tensor which is going to have a shape bigger than 32 in this case, right? So again, depends on you. What do you want to keep the max shape? But the general rule of thumb of how we follow it is just see what is the biggest payload that you're getting, and based on that, just put the value of the max shape parameter over here. So let's run this, and let's wait for a couple of seconds while the TensorRT engine is getting compiled. So let's just wait for a couple of seconds. If there are any questions, please feel free to put your questions on the chat window. I'll be happy to answer them. So there's a question that does TensorRT optimize over CUDA? That is absolutely correct. Yes, it optimizes over CUDA. Is PyTorch good for server deployment on large scale as compared to TensorFlow X? So again, I would suggest that if you want to do large scale inferencing, generally Triton is also a very good option than TensorFlow X, because TensorFlow will not allow you to serve PyTorch models. But in case of Triton, you don't have any dependency that if you want to keep it with TensorFlow, PyTorch, or any other framework. Also, you can serve these models even on GPUs via Triton, but TensorRT will not work in that case. If we don't have NVIDIA graphic card, can we run the model on Docker images? No. So all those Docker images will require the GPUs, and they are basically built for GPUs. So if you don't have a GPU, I'm not sure if the Docker images will run properly. Is the TensorRT highest, or is there an highest than TensorRT? I don't really understand that question, but What is Onyx? Okay, so Onyx is basically open neural network exchange. So it's like an intermediate representation of an intermediate representation uh, of the neural network graph. So take an example. If you want to move from say PyTorch, if you want to take your PyTorch model to TensorFlow model, how will you do that? Right, and that's where Onyx comes into the picture. So what it does, it converts the PyTorch model into the Onyx IR, which is the Onyx intermediate representation, and then from the Onyx IR you can basically convert that into a TensorFlow model. So it provides a great ecosystem of interoperability and to move it across across multiple frameworks. Is TensorRT works on DGX station? Absolutely. So TensorRT will work on any device that has a GPU, right? Again, can be a simple 1080 graphic card, or can be a V100 server or a DGX station also. At present, can torch model be deployed directly? So yes, torch models can be deployed directly, but remember one thing, you can't deploy the torch model as it is, that is the .pt file. You'll have to basically run torch script on top of that, and then you can take the torch script model and deploy it on Triton. Another question is, my friend doesn't have NVIDIA GPUs. He has Intel GPU and one has AMD. Will it work? No, it will not work, because all this is being done for the NVIDIA compiler, which is NVCC, and it won't work on Intel or either on AMD. Yes, Triton Inference Server will work irrespective of it being on CPU or CPU or GPU, but TensorRT and other things won't work. Okay, so we have our TensorRT engine file over here, which is model underscore fp16.engine, which has been created over here. So let me now also create the FP32 version of this. Right, so as you can see in the last, I've given a flag called --hyphen fp16. Now let's try to run this without the fp16 flag, and let's try to see what happens in that case. Okay, so I'm just going to remove the fp16 flag. I'm going to change the name of this engine file to fp32 and run it as it is. And I'll show you how the size of the model also gets reduced by half because of this. Okay, so the FP16 model, you'll notice it's of size 49 MB, right? If you look at the Onyx model, it is 98 MB. So you see, when you moved from FP32 to FP16, your model size decreased by half directly, right? So, and again, that's a great thing, because especially for embedded devices, you'll have a small form factor in which you can accommodate your model. So using FP16 is again de facto, and compiling it with TensorRT will give it more boost as well, by decreasing the overall memory footprint, plus also decreasing the compute requirement as well in terms of the G flops that are there. Will this entire workflow using NGC containers with CentOS, or is only for Ubuntu? It will work with CentOS, Ubuntu, seamlessly, or even with Red Hat for that matter. For fact. So it's not OS specific. It will run on any of the OS. Okay, so I think even this is done. So you'll notice that the model that has been generated, again the FP32 model is of a bigger size, right, compared to the Onyx model as well. So yep, so my the only takeaway that I wanted to give is, always optimize your model with floating point 16 when you're trying to do inferencing, and when you're training, do use the automatic mix precision and multi GPU for accelerating your workloads. I'll share the code base on the GitHub repo that Professor Pavitra mentioned. It might take some time, but we'll surely share it there along with the slides as well. So I think that was all that I had for today's session. At the end of this, I'll also share some links that might be helpful to all of you for getting more insights on the developer zone as well. I'm going to share my mail ID as well in case if anybody has any question or any queries or want to know about something, please let me know or just drop me a mail. Okay, so I think with that, uh, uh, that's all I had for the last 2 days. And again, I would like to thank IIT Kharagpur, NSM, and Professor Pabitra for having me here to present. And thank you, everyone, for being a great audience. Over to you, Professor Pabitra.
Thank you, Megh.